Am I audible?
Yes, sir.
Yes, sir.
Okay. let's start with the discussion. Am I audible? One more time, I am asking.
Yes, sir.
Okay.
Yes, sir.
So, can anyone quickly recap what we did last time? What we discussed?
So we discussed placement and
Yes.
in that 2D placement and 1D placement, and
Mhm.
then length of wire, how to calculate in different arrangement, and then some introduction about routing.
Okay. Thank you, Nirali. Good. So, we discuss the four major steps that we have to pass to generate the layout, useful layout for the foundry. So we are applying our netlist. We have to pass this netlist into four physical design steps, four major physical design steps. First is partitioning, second is floor plan, next is placement, and then routing. Intermediate steps not we discuss yet, but whenever we go for each individual chapter, definitely we'll see what are the intermediate steps to get the final output. So input is our netlist, circuit netlist, or we can say the which modules are there, what is the interconnection of modules, and output we call as a layout. Now once layout is available with us, immediately or directly it is not given to the foundry for the fabrication. There are some checkpoints are there that we are going to discuss. There are total 6 checkpoints are there, and we have to pass our layout for each and every checkpoints. And that process to checkpoint is called the sign off. So sign off engineers are also required in VLSI engineers that check the different possibilities of errors in the layout. Once your layout is passed after this sign off for checkpoints, then graphic data system, that file is generated, which we call as a GDS2 file. It's a binary file, graphic data system, and it is given to the foundry. So today we are going to discuss what are the checkpoints available in the sign off, as well as what are the initial steps start from the specification. That also we are going to discuss. Initial phase, how to generate this netlist. Okay, so that also we are going to generate, and this is complete identify as a VLSI design flow. Start from specifications to final GDS2. Of course, after fabrication, packaging and always there, and then after testing is also available. So once foundry fabricate the IC, that we have to test, okay, and then it is available for the customer once it is passed through the complete testing process. But the if your software compatibility, software knowledge, or this design VLSI design fails somewhere, definitely you have to work again and again to get the complete chip. So foundry people really rely on this VLSI design flow, where how to get in, how to get in into this unexpected output. So we are going to discuss checkpoints first, or sign off mechanism, and then we'll see what are the initial steps also there that we are going to see. So first checkpoints, once your tentative layout is ready, okay, it is checked with the very first and very important, that is called the DRC checkpoint. Someone know the full name? Can anyone quickly say DRC?
The design rule check.
Design rule check.
Yeah,
Design
exactly.
rule check.
Design rule check. So foundry also give These rules are given by the foundry. If then very general rules, this is called the lambda rule. Okay, all the foundries that follow this lambda rule. For example, if a MOS structure from the top, the layout is look like this. This is our diffusion region. And we have to place the polysilicon like this. This is my gate. Can anyone tell me how this layout of MOS look like? Why this? How it is available? Can anyone tell me? This is my MOS. Okay. If I am looking from the front, it is look like this. It's source and drain. P substrate. Okay. This is my channel length. Where is my width of the channel? Can anyone tell me?
The width of the diffusion.
So if I'm extracting this all the way to look for the 3D view, this is my gate oxide, and on the top we have a polysilicon gate, and then I expand in this way like this. So this is identified as the width of the MOSFET. So if you look from the top, we find that we have diffusion layer like this. This is my diffusion layer. This one. This entire rectangle. Okay, this one. So this is my W. Okay. This is my W, and at the top I have polysilicon also, polysilicon gate also, this one. So whenever polysilicon cross the diffusion, then and then transistor is created. One side we have source, other side we have drain, in between we have a gate. So this area is identified as a source, drain. You can interchange also, no problem, with metal contact. So this is my channel length. From the top view, I am looking from the top. Layout always you have to see from the top. So this is my channel length, this is my width. Now whenever foundry people say that these are the lambda rules, lambda rules is nothing but is a general terms. Channel length always you have to keep as a 2 lambda. Generic terms, lambda is L is 2 lambda, where lambda is L by 2. So if you are working in the 180 nm technology node, minimum channel length you can take as a 180 nanometer. That is my L. So L lambda is normally L by 2. So somehow if you design a layout and if you keep only for 1 lambda, or for 180 nm if you keep only half of this value, which is 90 nm, and there is a DRC error is there once you pass for the DRC check. So minimum channel length expectation from the foundry you keep 2 lambda. Same way with this width is also minimum value. Why we are discussing all value minimum? Can anyone tell me? Why all rules are based on minimum? Hello?
Area?
Yes, area is a constraint. I cannot design very big MOSFET, which there is no use and only the area is large. So all rules are defined as a minimum value. So L minimum you can take 2 lambda. Width of the MOSFET you can take as a 4 lambda. Okay. This length you can keep as a 12 lambda like this. This is 2 lambda by 2 lambda is a metal contact. Okay. So these rules are fixed. You cannot modify this. If your violate, you can violate. If your layout is violate this one, definitely you have to first recorrect your layout, and you have to find out that your DRC errors are 0. So there is a tool we call as a microwin. Okay, you are going to use this kind of concept for each and every experiments or any designs. You are going to check this DRC rule. We have to pass first checkpoint, which is called the DRC in the sign off. There are many rules. Same way for PMOS, we have these rules are available. We have an anvil, we have to place the anvil. For that, we have rules. We have to place the vias between two metals. It has to pass with some lambda rule. So these are the lambda DRC checks. If it is DRC error is there, definitely you have to modify your layout. So first checkpoint is available like this, DRC, design rule check. So in the software, these all facilities are there. This is the job done by the software. Only you have to say, you have to just click on that particular layout, particular design, and software will all identify there is a DRC error somewhere, for example, over here. Somewhere, let's say over here, your lambda is not 2 lambda, L is not 2 lambda, you have to modify, you have to increase or change. So based on that, this is the job for the software, but you have to pass your design with this DRC check error. Okay, is it clear, all of you?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So first checkpoint we discuss as a DRC design rule check. Once you are playing with the layout, this is the very first checkpoint. You cannot neglect this DRC error. Otherwise, foundry people are not able to fabricate your design. Next, we go very important step that is called LVS. Anyone know the full name? LVS.
Layout versus schematic.
Yes, Parthiv, I know that you have answered. So layout versus schematic is a very important step. So after designing the layout, and if you apply the LVS check, it from the layout, your software also generate the layout netlist. Your software also generate the layout netlist. And it will check that whether all connections are there in the layout according to the schematic diagram. There should not be any short circuit, there should not be any overlapping of the wires or the connections or the component. There should not be any opens in the connecting nets. There should not be any parameter mismatch. So if there is a parameter mismatch, definitely your design is not passed through the LVS. So three major sub checkpoints in the LVS. This layout netlist is compared with the circuit netlist. Okay. If both are same, then your LVS error are 0. So three major sub checkpoints. One is short circuit, one is the open circuit, and third one is the parameter mismatch. If the value of particular component is different in layout and it is also different in schematic, there should be definitely there is a report as a parameter mismatch. So you have to compare your layout netlist or layout with the parasitic. Just one, you have to compare with the layout netlist with the circuit netlist. That is our LVS, layout versus schematic checkpoint. So that is our third in the sign off stage. Okay, so that job is also done by the software. So let's move for the next one. That is the third one and also is equally important. parasitic extraction. Anyone having any idea about this word parasitic extraction? Somewhere in your BTech level or maybe parasitic. Every component, okay, any device we use, if that device is used at a high frequency, definitely internal or stray capacitance come into the picture. So that is called the parasitic resistance, parasitic capacitors, like that, passive components which effect is visible at the higher frequency. Can anyone tell me why it is visible at high frequency, not at low frequency? Hello?
So at low frequency capacitor, it look like open circuit.
X is 1 by 2 pi f equal to 0, X is infinity, open circuit. Okay. Okay, one answer. Any other answer? If you recall, we discussed this analogy. One is low frequency signal, second is high frequency signal. We are applying some input and we are looking the output. कुछ याद आया? Anyone recalling this? This is change in voltage across capacitor, VC. So if it is a low frequency signal, the effect is you can ignore that change in the output voltage. But if there is a high frequency, in very less time, that change you cannot ignore.
Yes, sir.
So high frequency, always that effect is available on the capacitor, and some components are there. You cannot ignore that effect at the high frequency. So whenever we design the layout, okay, with the help of software, we have to add the parasitic. We have to add the parasitic. This process is called the parasitic extraction. If you just do the simulation of your circuit, let's say here you get the circuits and you do the simulation, it is called pre-layout simulation. Before generating the layout, we are checking the simulation, that is called pre-layout simulation. But once you add the parasitic, definitely RLC are added, and then if you do the simulation, it is called the post-layout simulation. Is there any difference in post-layout and pre-layout? Result remains same. Suppose we are checking this some parameter, let's say speed. Yes, can anyone please say something? Pre-layout result is same as post-layout or different?
The different.
Why it is different?
So after adding parasitic capacitance, there will be a little bit difference.
Yes, exactly. In the pre-layout, just we check the without parasitic. We are not including the wire delay. We are not including any device capacitance, something at the higher frequency. But once we add the parasitic extraction manually with the help of the software, we are adding the parasitics and then we check, yes, this is my actual speed of the design. Okay. So at this stage also we are generating the netlist. There are multiple stages where we are generating the netlist, which is a which includes the parasitic also now in your design. So parasitic extraction is a major checkpoints where we can test actual speed of our design. Speed, area, and power. As I said, three major requirements for digital circuits. So speed is very important. So for that, we are looking this parasitic extraction. We are adding the components, parasitic components in our layout. This is possible with what microvin you are going to use in DVD lab. And that is a basic demo tools. But if you are using license tool, in that case, it is possible that you can add the parasitic. In Cadence Virtuoso, we have also facility to add the parasitic. In Cadence Encounter, we have also facility to add the parasitic extraction. So in the all license tool, it is there to check the parasitic. So that is the third checkpoint in the sign-off mechanism or for the layout testing, parasitic extraction. Number 4, IR drop analysis. Actually, for this all 6 checkpoints, different engineers are there. Suppose you are working in the DRC. So once your design is new, for that also you have to generate some DRC test file in such a way that your design is passed through that new DRC test file. If you are working in the layout versus schematic, only you have to check that step for any given design to you. So engineers are different for all these checkpoints. If it is a parasitic extractions, you have to modify the layout multiple times in such a way that you can satisfy the speed constraint. Now, fourth one is IR drop analysis. So we have a wire resistance, okay, and if we apply some voltage, definitely current starts to flow. In our VLSI, we call as a metal wire, okay. So definitely it follows the resistance. If we apply the voltage, current starts to flow. If very large value of current and R is available, there is a large voltage drop, which is unexpected. So somewhere if you require 0.5 volt and available because of this large value of I and large value of R, maybe 0.1 is available. So this drop you have to control, or you have to check. First you have to check and then you have to modify. So that analysis is called the IR drop analysis for each and every metals or each and every layers wire materials we are using in our design. So signal integrity is major problem. If your signal, if you are working with analog or any other domains, if your signal is like this, but if your expected output is look like this, the signal integrity because of change in the voltage, you cannot neglect that. For that, you have to perform the IR drop analysis. So that is the checkpoint number 4 in the process of sign off. So Cadence Encounter or many major tools that give Synopsys ICC compiler that also give this facility as a IR drop analysis. You have to pass your layout for this checkpoint. Number 5 is EMI EMC. Can anyone know full name?
The electromagnetic interference.
And electromagnetic compatibility. Suppose same kind of IC is fabricated or designed by some other companies, or it is designed by your own companies, and if you not pass with EMI EMC interference, definitely there is a change in the functionality because of this electromagnetic interference. And this effect is majorly because of the radiation. So if you are working, suppose this IC in the space where radiation effect is very large, so you have to design your layout, you have to design your circuit in such a way that there is no effect of radiation. It's called RHBD, radiation hardened by design. In the one of the project from the ISRO, the university IC department fabricated the IC for the RHBD applications, where that IC library cell is used in the space application where radiation effect is tolerated. So EMI, EMC is very important checkpoints. You have to avoid in specifically application like satellite or space applications where your IC is actually used there. Other way you can apply the specific package. Okay, so in that way also you can avoid the radiation effect. So your package is also important step where you can manage the radiation effect. Gold package like that. But cost you have to worry. So that is checkpoint number 5, EMI EMC test that we have to perform to avoid any radiation effect. If it is there, we have to modify our design. And the sixth and last one, anyone know full name?
Static timing analysis.
Yeah.
Okay, so for each and every path, we have to check the difference required arrival time minus actual arrival time. Required arrival time is given in the specifications, and actual arrival time you can find out from your design from the simulations. So if this difference is positive, this difference is called slack. Okay, the static timing analysis parameters. If this difference is positive, your required arrival time is large as compared to your actual arrival time, or in some cases also it is negative. Actually we require 0. At this difference we require ideally 0. So if this is a net, let's say this is a path, let me put the inverter. There are two net 1 and net 2. I am saying net 1 is critical net. What you understand by critical net? Critical net. Net 1 is critical. Net 2 is not critical.
Having largest delay.
Largest delay, yes. If net which has a largest delay, it's a critical net. Okay. So for that critical net, if you perform the static timing analysis, this difference is not 0. So in that case, to modify that, you have to add some buffer. Okay. Some buffers are added in such a way that you can avoid this difference. You can try to make that difference equal to 0. In our syllabus, we have one complete chapter to understand the fundamental of static timing analysis. What are the algorithms available to make this slack equal to 0? Called zero slack algorithms. So buffer insertion is one of the process. That process is also available once we see the cadence and counter, how we can perform the static timing analysis. So it's an important checkpoint. If there's a timing violation, definitely you have to avoid that timing violation because you have to meet the required speed of our design. So static timing analysis is checkpoint number 6 of the sign off. Once your design is passed through this all checkpoints, then finally you have to generate the binary file, the graphic data system, and that you have to give to the foundry. Foundry people fabricate that IC on the silicon, and it is checked by the testing process, and then it is available finally for the applications. So in this course, our syllabus is available up to this. Start from circuit netlist as input, VLSI physical design, We have to pass our design for this checkpoint also, and sub steps as well as these are the abstract steps: partitioning, floor plan, placement, routing. But in detail, we have pin assignment also and many other clock routing, detailed routings. We have to pass through this all the steps as well as all the checkpoints, and then we can say yes, this is our final layout. So in the laboratory, we are going to generate the final GDS2, but before that, sign off steps also, as well as this physical design steps like partitioning, floor plan, placement, and routing also that we have to perform. So in the theory class, we are going to check different algorithms. We are going to see the different algorithms for each and every steps. In the laboratory, we are going to perform these steps by the software. That is for the entire course. Any doubt in this, or shall we move ahead?
Sir, on what basis we select DRC rules?
So as I said that this is foundry requirement. You cannot violate the foundry requirement. They say that channel length at least 2 lambda. So if you are working in the 180 nm minimum channel length, you have to keep 180 nanometer. W of diffusion is 4 lambda. So these are the fixed rule. You cannot violate, you cannot avoid that rules. So if you pick up any software, these rules are predefined from the foundry, channel length, W, metal contacts, like that. If you pick up your diffusion 3 lambda, definitely it gives the DRC error. If you pick up your channel length 1 lambda, definitely it gives the error. The minimum you have to use. Is it clear?
Yes, sir.
Okay. So now we discuss the initial few steps, how the circuit netlist is generated. Okay. So initial steps look like this. After the specification, maybe in other course also you know. Okay. That is called the design idea, design requirements. Okay. Which is first passed to the behavioral design. Behavioral designs include the flow graph, pseudo codes, some coding is included over here. The behavioral level designs. Then it is passed through the data path design. Which is called bus or register structure, RTL level. Then logic design is available. Okay. And then you have to synthesize your logic design to generate the gate level netlist. Once you have gate level netlist, where is a transistor, physical transistor, NMOS, PMOS? Because at this stage we have a gates, logical gates. Where are the transistors available?
At structural level.
Structure, there are 3 ways you can write VSDL Verilog. I am not added that part. But once anyhow, with any case, maybe behavior or maybe data or maybe structure, but you finally have logic design where gates are available. So whenever you do the logic synthesis, you have to add the foundry file. Okay. Foundry, let me 180 nm, 45 nanometers, where your actual metals, transistors are available. So if you are performing the, let's say on Xilinx ISC, okay, where also you can do the logic synthesis. But at that time, for once you select particular FPGA, based on that your delay area and speeds are available, that reports. I think you started installing that software and maybe next week you start writing the code, and then once you do the logic synthesis, that is only for specific selected FPGA. But here in this ASIC design flow, application specific integrated circuits design flow, you have to add the foundry based on your design requirements. So once you add the foundry, all metals, metal weights, everything comes into that foundry file. So it's a logic in the software, we have to add this file with the logic designs, and then we get the accurate report. What is the speed, area, and power? So once it is there, we have a netlist is generated that we pass to our physical design. And then as usual, what we discuss over here for the foundry, GDS2 for testing like that. So let us see the example of this behavior level, how we can play with some flow graph mechanism. Let's say I am taking one function a equal to b cross c plus d. Can anyone sketch flow graph of this function at behavioral level? So I have a b, I have a c that I have to multiply, and in that I have to add the d, and this is my a. This is flow graph, okay, at the behavioral level. Or if I have some condition, let's say if condition a is there, then and then you have to pass, or you have to go at, let's say, S1 stage, else you have to pass at S2 stage. For same one, you can also gauge the flow like this. If it is true, you have to go in this direction. If it is false, you have to go in this direction, then S2 and S1. Okay, this is data flow graph. Okay, this is data flow graph. So this is at the top layer where we are actually writing the VSDR Verilog or system Verilog kind of stuff at the top level after the specifications. If you are working same function at the register or RTL level, it look like this. Let's say you store some variable, B variable in register R1. You store some C variable in register R2. Then you have some multiplier function, because our requirement is B cross C. So here some multiplier function, and you have register R3 where you store the result, and then you have an addition function also where you do the addition of D, which is also there in the register. Let's say R4, and this output I have to apply, okay, as a final result. So this is identified as a RTL level. Okay, so the design steps at the RTL level, how your design of simple function is look like. Once you generate the logic, if you use for logic gates for all this purpose, multiplier, all this R2, R1 register level, your logic design is generated. Once your logic design is there, maybe like this, with some flip-flop, some gates, for example. Okay, this is my logic design, and then you have to do the simulation, which generates the gate level netlist. If it is gate level designs, we can definitely go for the transistor level designs, something like this. Once we have this transistor level designs, definitely we go for the layout like this. PMOS at top, bottom is NMOS. But this is not limited. This is our design is not limited up to this 1, 2, and 3. Okay, our design is available with large number of gates, large number of transistors. So if that is the case, we have to pass into this kind of process. If I am saying that design the layout for NOR gate inverter only require 2 transistors. So in that case, no need to pass with partitioning, floor plan, placement, routing. The manually without software also with pen and paper you can sketch, and then same you can duplicate in your software and you can generate the GDS2. But if it is a complex design, all the designs nowadays are complex, not very simple basic like half header, full header. We have to take the help of this software, or we have to pass our design into this step-by-step process: partitioning, floor plan, placement, routing. So this way, entire design process, VLSI designs process start from specification to final end user. So in AMSVD, analog and mixed signal design, where limited number of transistors are there, 1 transistor, 2 transistor, 3 transistor, maybe let's say 10 transistor. So no need to pass your design into this all the steps to generate the layout. You can design the custom layout also, and this what layout we are going to generate over here, that is generated by the tool. Okay, but that is possible with the algorithm. If it is a microwin tool, directly you can generate the custom, or you can sketch the custom layout. K layout is also one of the tool where you can generate the custom layout. Custom, it means this designed by the user, but it is there only for the small design, not for the complex design. And our task, our mobile is not only for 1 gate or 2 gate, millions of gates, millions of transistors. So definitely we have to learn all these design steps in detail with different algorithms. So now your turn, you have to ask question. If you have any doubt, you can ask.
Also,
Yes,
the
Rupam.
difference in behavior modeling, data flow.
So the way you are writing your VSDL Verilog code, you can write at behavioral level, you can write at the functional level, you can write at the structural level, like that. But ultimate output, final output is your logic design. Okay. So whenever you start your programming, okay, in the one of the lab, I forget the name, programming language, that kind of course is there. Anyone know full name?
The ADS DPL.
Yeah, yes, correct. In that you have Xilinx ISC, Model C. You can, yeah, they will definitely write the Verilog code, or you can even start with VSDL also first, then Verilog system, Verilog. These possibilities are there. Yes, more question.
Sir, what was the second step for sign off?
Second step after sign off or number 2?
No, yes, sir. Sign
This
off,
one,
no, sir. Yes,
this
sir.
one. This
Yes,
is
sir.
LVS. This is DRC. This is parasitic extraction.
Yes, sir. The LVS one, sir.
Yeah, layout versus schematic. So whenever we generate this kind of layout, okay, we have to generate the layout netlist. This layout netlist we have to compare with the circuit netlist somewhere over here. Okay, or maybe gate netlist. We are working at the gate level. So if there is any short circuit like that, if there is any open circuit between two transistor, wires are connected or not, that we have to compare our layout with our schematic. Just by looking the very complex layout, you cannot say this is my transistor connection like that. At present, there are only two transistors in this layout. One is PMOS and one is NMOS. And perfectly it is connected, but somehow let's say it is open at here. You say millions of transistor and connection is there. Manually you cannot check which wire is left for connection and like that. So this netlist, this process, LVS process helps to match your schematic with the layout. All components are utilized or not, all connection properly there or not, if any connection is left or not like that. So it is there as a LVS step, layout versus schematic. Is it fine? Okay. Yes, more questions. This is the one of the topic, that is VLSI design flow or process steps in the physical design, the chapter number 1. If you recall the LMS, I uploaded syllabus for all the courses, lab manual also, and lesson plan also. Everything is there on LMS. Anyone try LMS?
Yes, sir.
Yes,
Okay.
sir.
So at present we are on chapter number 1, which is basic introduction, how the steps are available. This is first point in this chapter number 1, introduction of physical design, where we discuss all the steps in very abstract level, in very brief, with some numbers, examples. Today in the lab also we are going to perform some tasks. So if you have a MATLAB install in the laptop or in your desktop, it's fine. Otherwise we can use online MATLAB also, where we are going to start with some graph theory, how graphs are useful, how graphs you can design for the given circuits. That stuff we are going to start, which is the first experiment as per the lab manual. So online MATLAB we definitely going to use. No need to install. If it is installed previously in your BTech, no problem. Yes, any more questions? Yes, Subham.
No, sir, we don't have question.
So this is your initial specifications and your VHDL Verilog, that kind of stuff. Logic synthesis, functional verification, whether your gates are working based on your requirement or not. That steps. So whenever we start the cadence encounter, we'll start with this initial step also. We generate some netlist, we simulate like your VHDL Verilog code, and then we take as an input for our next steps for the physical design. So cadence encounter we are going to use. I will give you the remote access for all 10 license to you. So Mobi Xterm, if is possible, let me give you have to install any DEX. It's freely available. Just type any DEX for Windows, you can download very easily. So just install this AnyDesk also, because after 2 or 3 labs we have to use the cadence encounter. AnyDesk, that is for the remote access. So next week we start with some terminology which is commonly used in the physical design. Once all terminologies are over, then we enter into the first step, which is the circuit partitioning with different algorithms. So probably in the next week we start the first step of our VLSI physical design partitioning, circuit partitioning.
Sir, will you send the PDF of the book?
You are not getting that PDF.
No.
So if you type the title, if you search the publisher where it gives the DOI number.
Okay, sir.
Once your DOI number, use this website science.hub.
Sir, can you write this site name on chat box?
sci.hub, science hub hub. Or you can write down in Google Science Hub. You will get first or second link where you have to enter the DOI and freely you can download the PDF. As a copyright issue, I cannot give you the PDF of any book, but I give you the process where you can. So see you at 2:10 with laptop. We start with the laboratory experiment.
Hello, sir.
Yes.
Sir, I have the MATLAB 2012 version in my laptop. So, sir, is
Yes,
this
okay.
version?
Okay, no problem. It will work.
Okay, sir. Thank you, sir.
Or online MATLAB nowadays also there. No need to install to save the space and everything. Memory requirement. Online facilities there. Okay, we'll see you at 2:10.